In this lecture, I will explain model diagnostics for linear models, including ANOVA. First, let's discuss when you should use model diagnostics. If you want to draw conclusions of causality, then you need an interventional study. And for interventional studies, the correct workflow is usually as follows. First, you define a research question, and then you choose a test or model that can answer this research question. And this is why model diagnostics are required, because every test or model comes with a set of assumptions, and we're going to see if those assumptions actually hold up in the sample. Then we design a study or experiment, and finally we collect the data and perform the analysis with the proposed test or model. Only after you've performed this step can you perform model diagnostics, to see if the assumptions that you made were actually reasonable. Finally then, if no large deviations from the assumptions are found, you can draw conclusions from the output of your test or model. Next, let's discuss what model diagnostics are. So even if you have a solid theoretical basis for the assumptions that you make, they can still turn out to be incorrect in your sample. Model diagnostics are therefore visual and numeric guides to help decide whether the assumptions that you made actually hold up. And they can also provide an indication of why an assumption does not hold up. Model diagnostics are often confused for things that they're not. For example, you cannot conclude that your assumption was correct based on model diagnostics, because you have no evidence for this. And also, you can also not decide that a model is right or wrong. It can still be misspecified, even though it meets the assumptions. The difference may sound subtle, but it is important. Assumptions have to be based on theory. No test or visual diagnostic can help you decide which assumptions to choose, only whether the assumptions that you find reasonable actually hold up in the sample. For linear models, and ANOVA is also a linear model, so also for ANOVA, the following assumptions can be checked with model diagnostics. First, we can check linearity. We can also check the normality of the error term and constant variance of the error term, which is also known as homoscedasticity. Linear regression makes no assumption about outliers, but they can be very influential to the coefficients, and therefore we also look for leverage and outlyingness. Let's discuss linearity of the relationship first. A linear model simply assumes that the relationship between the response and the explanatory variables is linear. This doesn't necessarily mean that there is a line, but it does mean that the relationship can be expressed in terms of intercepts and slopes. If there's only a single explanatory variable, then the resulting model would be a line, so you can get a reasonable idea of linearity just by plotting x against y. And you can see two examples here, where the left clearly shows a linear relationship, and the right shows a quadratic relationship, which is not linear. A better way and a more general way to assess linearity is using the residuals versus fitted plot. It shows the differences from the regression line, so the residuals, against the regression line itself, which is called the fitted values in the plot. If there is a strong trend in the residuals, then that means there is a strong deviation from linearity. So what this plot really shows is, in the previous plot, if we would fit a line to these data, and we subtract from that line the intercept and the slope, we subtract from all the observations the intercept and the slope, then what is left behind is a line centered around 0 that is flat, and we're going to look whether the deviations from this line go up or go down in a trend. Now, for this first example, where there's clearly a linear trend, we see no clear trend in the residuals versus fitted plot, which is a good sign. However, for this quadratic trend, we can clearly see that what we saw over here is also shown over here in a different way once we fit a line to it. You can simply create this plot by fitting a linear model and then using a plot model and which is equal to 1, and that will give you the residuals versus fitted plot. If you do detect a strong deviation from linearity, then the next step would be to perform a transformation to see if the resulting relationship is linear. I will go into more detail on how to do this at the end of this lecture. But in short, if for example you see a strong quadratic relationship, then all you really have to do is fit a model that captures this quadratic relationship. So I means as is, because this term is already reserved for interactions. So instead of fitting y against x, this model fits y against the square of x. And when we do that and we plot the same residuals versus fitted plot, you'll see that this trend over here is gone. Next, we're going to talk about normality of the error term. You can check this using a QQ plot. So a linear model assumes that if you subtract all the effects of the explanatory variables, then what remains must be normally distributed noise. Now, what this plot shows is a theoretical normal distribution on one axis plotted against the standardized residuals on the other axis. And what we want is ideally for the observations to very closely follow the line that represents the normal distribution. If the deviations are strong, especially around the center, or if there is a strong trend in this plot, then that means that these data are not normally distributed. These residuals are not normally distributed. So this example, I simulated data from a normal distribution, and you can see that still it deviates here and there, so small deviations can be ignored. And here I've simulated Poisson distributed data, which is the distribution of independent counts, and you can see that there's somewhat of a staircase appearing and large gaps in between. The overall shape does not represent the line. You can create this plot using plot model and then which is equal to 2. But there's a problem with this, and that is that it is very subjective whether these differences are large or small. And you might not agree with me that this is a small deviation and this is a large deviation. And for that reason, I recommend that instead you use the same function, QQ-plots, but from the package car. When you do this, it will also compute bootstrapped confidence intervals, which give you an indication of how severe the violation is. And in this case, the first line we see, example, we see that the data nicely follow more or less within the confidence bands of the normal distribution. But for the Poisson distributed data, we see very clearly that there is a trend in the data and that a lot of the observations fall outside the confidence bands, especially around the center, but also in the tails. You can do this by installing the package car, which might give you some issues on Mac recently, but if not, then all you have to do is install car, then do require car, and then you need to supply a data argument to your linear models. You can't just do y against x because this function QQ-plot expects there to be data supplied to this model. And when you do that, you can simply do QQ-plot model, and that will give you the QQ-plot shown above. Even with confidence intervals, it can still be hard to figure out what is going on based on a QQ-plot alone. You've only concluded that the residuals aren't normally distributed, but that doesn't necessarily mean that the problem is non-normality. It could also be that you've left out an important explanatory variable, that the relationship isn't linear, or even just that there's an outlier. So with that in mind, here are some simple guidelines. First, the center of the plot is more important than the tails. Especially if there's only one or a few deviations in the tails, then you can usually ignore those. And second, a trend is more important than one or a few deviations. So even if you see a deviation in the center, try to see if there's an overall trend occurring where it doesn't follow the line, rather than there is a single observation that is very close or just beyond the confidence intervals. There's also a very nice post on Cross-Validated, a statistics Q&A that explains how to interpret a QQ-plot. So if you simply Google this question, you will find it on Cross-Validated. And there's several answers here that are very nice and go into a lot of depth into what you can conclude from a QQ-plot, and also why it can sometimes be difficult to make conclusions from it. In cases where it's hard to decide based on a plot alone, it is also possible to use a significance test for deviations from normality, like the Shapiro-Wilks test, which you've probably used before. In this case, you simply fit a model and then perform a Shapiro test on the residuals of the model. Then you see whether the p-value is lower than your alpha, and if it is, there is a significant deviation from normality. However, as with all diagnostic tests, you have to keep in mind that a significant test doesn't necessarily mean that the violation is severe. And also, if the test is insignificant, you cannot interpret that as evidence that the assumption is correct. And lastly, if you perform significance tests for all your assumptions, then you have a lot of chances of a false positive. So the overall chance of at least one significant deviation will increase. And therefore, a lot of people recommend that you don't do significance testing for diagnostics. If there is a strong deviation from normality, then what will happen is that the model does not produce accurate standard errors, t-values, and p-values. And when this is the case, you should try and determine if the assumption is violated because of a different issue. That's the first thing. So maybe there's nonlinearity, maybe there's an outlier, etc. But if your data truly come from a known non-normal distribution, then you should probably not use a normal linear model in the first place. And that is what you will learn when you learn about GLMs in Chapter 3 of Elements of Biostatistics, where you start by choosing a candidate distribution. So you would choose normal for when there is a large independent sum of effects, and you would use Poisson for counts, and you would use binomial for ratios, etc. Next, let's discuss the constant variance of the error term, which is also called homoscedasticity. So, in a linear model, we assume that when you fit a regression model, then the deviations from this model are more or less spread the same, whether you are low or whether you are high on the fitted values. So for a single explanatory variable, that means that along the values of x, you would expect the variance to be the same of y. You can check this with a scale location plot. So here I've plotted two examples again. The first one is a model where the variance is perfectly constant, and you can see that there is no real trend going on, and there's the variance around the regression line is more or less the same everywhere. And in the second plot, I have simulated data that has very strong non-constant variance. And you can observe two things here. First, the red smoothing line is slowly going up, which means that the variance is going up. And second, you can see a cone shape, which means that over here the data are clustered very tightly. Over here there's a much larger spread, so a cone like this appears. You can create this plot using a plot model again, and then you choose which is equal to 3. And what you want to look for is either an upwards trend or a cone shape in the residuals. If there is non-constant variance, then this cone shape that I just discussed is usually also visible in the residuals versus fitted plot. So this is the first of the diagnostic plots that I discussed, where you do which is equal to 1. And again, you can see that if there's no non-constant variance, then you should see nothing. But if there is non-constant variance, then what you'll see is a kind of cone shape where the variance is very, very small on one end of the plot and a lot larger on the other end of the plot. Again, if you're not quite sure whether there is heteroscedasticity or not based on the plot, then it is possible to use a significance test. And in particular, a lot of people use the Bruce-Pagan test. You can use the built-in test in R, non-constant variance, NCV test, or I think it's from the package car. But a more robust version of the test is the studentized Bruce-Pagan test, and that's included in the package LM test. Again, if you have problems installing it, you can look for an alternative, but this is a very nice test that is a lot more robust than the other ones out there. And again, if you have a p-value that is small enough, then you reject the assumption that there is constant variance, and you have to look for an alternative model. But again, keep in mind that even if it is significant, that doesn't mean that the deviation is necessarily severe. So you still have to look at the diagnostic plots. And if the p-value is greater than your chosen alpha, then that doesn't mean that the errors have a constant variance. And also, if you perform multiple significance tests, so let's say that you already checked for normality and you checked for linearity, and now you're checking for this one, that's already 3 chances to get a false positive. So the overall chance that at least one of them is significant, even though there is no violation in the model, will increase. Lastly, let's discuss leverage and outlyingness, which can have a very large influence on the coefficients. So if you have a single outlier or a small set of observations that are very far away from the rest of the data, or that have a outlying value in one of the explanatory variables, then that can have a undesirably strong impact on the estimated coefficients. And you can very simply assess this through the residuals versus leverage plot. And what it shows is a dashed line, which is the Cook's distance, and the first of which is the border of a half, and the second of which is the border of 1. And what you simply want to look for is whether any of the observations fall beyond these borders. Now, if they do, and they're beyond the first border, then that is considered anomalous. And if they're beyond the second border, so greater than 1, that is considered outlying. But even if an observation is outlying, it can still correspond to the rest of the trend in the data. And if that's the case, then it doesn't have very high leverage. But if it also pulls the estimates towards it, so it's not only outlying, but it's also suggesting a different coefficient than the rest of the data, then it also has high leverage. And again, it's also possible for an observation to have very high leverage, so it's pulling really hard on the estimates, even though it isn't outlying. Now, you can create this plot using a plot model and then which is 5, and that will give you the residuals versus leverage plot. And what you want to look for is observations that are both outlying and have high leverage, because those are the most problematic. When you do encounter an outlier, you should always consult your lab journal or some other source of metadata to see if you can logically explain why an observation is outlying. For example, a systolic blood pressure of 200 milliliters of, that should be small letter G, 200 milliliters of mercury is most likely, statistically speaking, an outlier, and you'll see it in the plot. But it is certainly possible if your study includes patients with hypertension. But yeah, systolic blood pressure of 20 or 2000 is not possible in a living human being, so that is likely a faulty recording. And another example, let's say that you're counting bacterial colonies and you accidentally dropped a plate somewhere during the experiment, then that can cause changes, for example, contamination, that could explain later outlyingness during the analysis. Now, when this is the case, or when a decimal operator has been misplaced, then that is a reason to exclude data. So that's the only reason you should remove outliers. If you have outliers but you don't know why that observation is outlying, then you can't just remove it from the data, because it might actually be a very important part of your conclusion. So if that is the case and you're still worried about the observation having too large an influence on the coefficients, then you should look for robust linear regression. So in summary, we've seen the residuals versus leverage plot, which can be used to check the linearity assumption and the constant error variance assumption. When there's a clear trend in the plot or a cone shape, that is indicative of problems. The QQ plot can be used to check deviations from normally distributed errors, although you should always keep in mind that the cause can be something else, like an outlier or nonlinearity. The scale location plot can be used to check the assumption of constant error variance, and when there's a clear trend in the plot or a cone shape, then that is indicative of problems, so non-constant variance. And finally, outliers can be detected with the residuals versus leverage plot, where what you're looking for is whether any of the observations fall beyond the distance of 0.5 of Cook's distance, which is at least worthy of further inspection, or greater than 1, which means that it's actually problematic. Especially when an outlier also has high leverage, then you should do something about the outlier. For more details on the diagnostic plots, you can look at the book Elements of Biostatistics at paragraph 2.3. So then what do you do when any of the diagnostic plots or any of the tests reveal a problem? So in case of nonlinearity, the first thing to do would be to try a transformation. And in case of nonlinearity, what you would really want to do is use a generalized linear model or a generalized additive model with an appropriate error structure, but that's something I haven't discussed yet. And in case of non-constant variance, there's often also non-linearity. So if that's the case, you should try transformation, and otherwise you can use a form of robust linear regression. Finally, in case of an outlier, the first thing to do is to consider the reason the observation might be outlying. You can remove it if it is a corrupt entry, or you can refit the data with robust regression if there's no reason to remove the outlier. You should also note that even though I've discussed these 4 issues separately, they often aren't separate issues. And when you change the model to solve one problem, this will affect all of the diagnostic plots, so you should check the other ones again. And you should always aim for a change to your model or a transformation that fixes all problems at once in the diagnostic plots. Finally then, let's go into a little bit more detail about transformation. So transformation is really simple. All you do is you choose a transformed explanatory variable to see if the nonlinearity is resolved. So here we have a very clear nonlinear relationship when we plot y against x, but when we fit y against the square of x, then the nonlinear relationship is gone, so we can simply use a linear model. So there's always some transformation that will yield a linear relationship. Maybe very complex, but there's always something that would work. But the proposed transformation should also make sense from a biological point of view, because transformation will make your model a lot harder to interpret. So, for example, if you're looking at the surface area of leaves and you're measuring the length of the leaf, then that would be a very clear reason to use a squared transformation, because the surface area increases quadratically with length. Also, if you're looking at bacterial growth during the exponential phase, then you might want to use a power transformation, like 2 to the power of x, because that implies doubling. And when you're looking at drug effectiveness, there's usually a plateau where if you keep increasing the concentration, then there will be diminishing returns as to the effectiveness of the drug. And this is something you could model with a logarithmic transformation. So even if you have a justification for transformation, it can sometimes be hard to decide between candidate transformations that have a similar effect. For example, the logarithm and the square root both incur a plateau in the data, but yeah, which is better is not something that you can easily answer. So to help decide on which transformation to use, you can use the Box-Cox set of power transformations. So what this does is it shows a 95% confidence interval plotted over here with a point estimate in the center, and everything that falls within this confidence interval is a viable transformation of the response variable. Now, this is a package that comes pre-installed with R, so you can simply do require mass, and then do a model that has a problem that you want to transform, and then do Box-Cox of this model, and you will get this plot. So once you have the plot, what you want to do is look for the nearest value in this table and use that as a transformation of the response variable. So for reasons that I go into detail in the book, you don't want to use a transformation of 0.543, whatever this is, but instead you would want to use something, a nice fraction, like a half. So if a half is included in a plot like this, then you could use the square root of y. Or you could use the square of x, which has the same effect, more or less. And as for these other values, if another value is included in a 95% confidence interval, then you want to use the ones suggested over here. If multiple are included in the confidence interval, then Box-Cox cannot give you the answer to which is better. And also, if 1 is included in a confidence interval, well, if you do something to the power of 1, then nothing happens. So if this range over here includes 1, then you should not perform a transformation. For further details about transformation, see 2.4.2, particularly about Box-Cox. And for the visual diagnostics, see 2.3. And that is all for this mini lecture.